Alright, in this video we're going to talk about solving linear systems. I'm sure you've had some experience in solving systems of linear equations, but in this video we're going to try to look at this process in a general way to really understand what's going on and to automate the process. We're going to develop what you call an algorithm, which is something that you can teach the computer to do. So we're going to solve systems of linear equations in such a way that the solution can be programmed on a computer. All right. The method that is used is called Gauss's method. And for some definitions, a linear combination of the variables x1 through xn has the following form. Note that each term in this expression has a variable to the power 1. Okay, for instance, if this was x1 squared, that would no longer be linear. So I'll get rid of the square. In some way, this expression is reminiscent of the equation of a line, so that's one reason it's called linear. There are other reasons as well that we'll see later. Okay, these numbers a are called the coefficients. Here's one particular example of a linear combination. A1 is 1/4, A2 is 1, A3 is -1. And of course, instead of variables x1, x2, x3, I'm using x, y, and z. The particular names of the variables doesn't really matter. The only thing that matters is the form of the expression. Okay? A linear equation has the following form. You have a linear expression on the left, a linear combination of variables on the left, and on the right you have a constant. Okay? Now, if we have a n tuple, that is I think you are familiar with the term vector. This is a vector with n entries, and we can consider that as an element of n-dimensional space. Now, this collection of n numbers is a solution of such an equation if you substitute the s's in for the x's, and you get a true statement. Okay? And that's the solution for a particular linear equation. The solution for a system of linear equations would be an n tuple, that is a series of n numbers, such that this series of n numbers is a solution for all of these equations in this group. Okay? So here's an example. If we have three linear equations, so this was the equation we saw before. This also is a linear equation, linear combination here, constant here. Here's another linear equation, linear combination here, constant here. Okay. Now, if we wanted to find the solution to this system, we're looking for a set of three numbers, so that if I plug the three numbers in for x, y, and z consecutively, then I'll get true equations for each of these three equations. Okay. In order to find the solution, let's transform this system of equations. We're going to manipulate these equations using algebra. Okay. So we start by clearing the fraction. It's always better to deal with integers rather than fractions. So this indicates the operation that was performed to obtain this new system of equations. For row 1, this is the Greek letter rho here. This means I multiply the row 1 by 4. Okay, no pun intended. This row stands for the first row. Okay. If I multiply the first row by 4, I get 1x plus 4y minus 4z equals 0. And the other two equations are not changed at this point. Okay. Now, once I've done this, I can simplify further. Notice that the first two equations are quite similar. And if I subtract the first equation from the second equation, that's expressed by this operation here. I take row 2 minus row 1. If I do that, you can see that the x's will cancel, the 4y's will cancel. If I take 2 minus 4, I get plus 6z. Okay, so in this way I have simplified the second row to eliminate the x term, and in fact in this case I've eliminated the y term as well. Right? If I go to the last row, similarly I can eliminate the x term from the last row by subtracting 2 times row 1 from row 3. And that's what this operation indicates. Row 3 minus 2 times row 1. You can work out the algebra. The result will be this equation here. Okay. So, if you notice here, the equation here, 6z equals 12, that can be solved immediately. And the way we do this is we solve the equations from the bottom up. So I'm going to move this to the bottom position. And I do that by switching these two equations. All right, so this indicates the switch of the last two equations. I haven't changed the equations themselves, I've just changed the order. All right, let's go on. Now I can solve the bottom row z equals 2 by dividing both sides by 6. All right. Now, the shape of the transform system lets us solving for y by substituting into the second row. All right, see, now I know that z equals 2 from here. And I can put the 2 in here for this z here. Okay? Okay. And once I do that, I only have the unknown y in the second equation, and I can solve that to find y equals 1. All right? All right, once I know y and z, then I can plug the value of y in here and the value of z in here, and then I have an equation only with x. Okay? And once you do that, you get x equals 4. So I think this process may be familiar to you. What's important here is that we've set it out systematically, so we can have a well-defined process. All right. The definition: in each row of a system, the first variable with non-zero coefficient is the row's leading variable. Okay. A system is in echelon form if each leading variable is to the right of the leading variable in the row above it, except for the leading variable in the first row and any all zero rows at the bottom. All right. So what is this definition saying? In this particular example, what are the leading variables? Well, leading variable is the first variable in the row. Leading variable of the first row is x. Leading variable of the second row is y. Leading variable of the third row is z. And you notice that in this case, the leading variable of each consecutive row is to the right of the leading variable in the previous row. So in fact, this system of equations does satisfy the conditions for a system in echelon form. There's some various special cases here that we'll run into later, but suffice it to say, in this particular example, we do have a system of equations in echelon form. Okay. Let's do another example with 4 equations. Here we have, notice here that we have x, and here we have a gap. You can think of that as plus 0y. So it still has the same form of the other equations. This we can consider down here as plus 0x plus y, etc. And now we want to simplify. If you remember, in the last system of equations, the way we simplified was by eliminating the variable x from all the equations except the first equation. The way I can do that in this case is I can take this second equation and subtract 1/2 times the first equation. That's expressed by this operation here. And I can eliminate the x from this equation by taking the third equation and subtracting the first equation. That's expressed by this operation here. I don't need to eliminate x from this equation because it's already gone. The result of these operations gives me this system of equations. I can act on this system of equations. What we did last time was, after we had eliminated x from these equations here, we eliminate y from the equations past the second equation. So notice that in this case we have first equation, second equation. This is in row echelon form because the leading variables are stair-stepping, moving to the right. Unfortunately, in this case, this y is not to the right of this y, so we need to do some more operations to get the rest of this in row echelon form. It seems pretty clear that what I want to do here is exchange these two rows and then I can eliminate the y by combining this row with the second row. And let's see what happens here. Okay, so here we have 2x. So this row stays the same. This row stays the same. All right. He didn't exchange the rows yet. He just directly did the operation. It doesn't really matter if you exchange first or second. In this case, the combination of row 4 minus 2/3 times row 2 is going to give us an equation in the last position that has no y. Notice this minus 2/3, the relationship between the minus 2/3 and the coefficients here. It turns out that this minus 2/3 is minus 1/3/2. That's kind of interesting, isn't it? Okay, so let's go down and see what we do now. Now we still don't have this stair stepping because this w is not to the right of the z, but if we just exchange the rows we get this stair stepping effect. At this point we can zip our way back up and solve for the variables one by one. W equals -1. Once I know w, I can plug -1 into this equation and find z. Once I know w and z, I can plug w and z into this equation and find y, etc., etc. So that's what we say here. Fourth equation says w equals -1. Substitute back into the third equation, gives z equals 2. Then substitute back into second and first gives me y and x. So we get a solution 1, 0, 2, -1. Now, he says here that this solution is unique. Now, why is it unique? Well, if you go through all of these steps, you can also take these steps backwards. Any solution of this system will also be a solution of this system, will also be a solution of this system, etc., etc., will also be a solution of the original system. The reason that I can do this is that each one of these steps that I have taken is reversible, and we'll talk more about that later. It's clear that the only possible solution to this system is this set of 4 numbers. Why is that? Well, because w has to be -1. If w has to be -1, then z has to be 2, etc., etc. Okay, so that's why we can say that this is a unique solution for this system of equations. Okay. All right, so we expressed this in a theorem. We've done a particular example, but this can be done in general. So the theorem states that if a linear system is changed to another by one of these operations, and these are the operations that we have used in the preceding examples, if we make this change, then the two systems have the same set of solutions. Okay? These 3 operations are called elementary reduction operations or row operations. The 3 operations are swapping, exchanging 2 equations, multiplying by a scalar. If you remember our very first example, we eliminated the denominator, the 4 in the denominator, by multiplying by 4, so that's another legal operation, and row combination. Row combination means you take one row and you add or subtract a multiple of another row. Okay. All right, so here we go through the proof. So we verify the proof for operation 1. The other 2 examples are similar. So consider a general linear system. This is the general form for a linear system. All right, now this set of n numbers, S1 through Sn, satisfies this system if and only if, by substituting the s's in for the x's, then we get a set of true statements, that every one of these statements will be true. Okay. Now this seems a little confusing because we've just exchanged s for x, x for s, but you should think of x as a variable and s is a representation of any constant. So you should think of this not as a linear equation, but as a combination of actual numbers. Okay? Okay, in a list of statements joined with and, we can rearrange the order of the statements. Okay, if you say 1 plus x equals 2 and 2 plus x equals 3, I could say that in the other order. I could say 2 plus x equals 3 and 1 plus x equals 2. That doesn't change the solution for x. Okay, so if I list the equations in a different order, that's the same thing as swapping the rows in the set of equations. Okay? So in this case, we can see that swapping rows doesn't change the s's that satisfy the m different equations. Okay? Now, it's possible to have a system of equations without a unique solution. All right? For example, here we have a system of 3 equations, and it's not too difficult to show that this system has no solution. Okay? So if we take, on the left-hand side, if we take the sum of the first 2 rows, that's equal to the third row. But on the right-hand side, that is not so. Let's verify that. Okay, here we have x plus x equals 2x, y plus 2y equals 3y, z plus z equals 2z. Okay, so if I add these 2 equations, I get on the left-hand side the same expression as this expression. Unfortunately, if I add the 2 constants on the right-hand side, I don't get the same constant as over here. Now we know that if x, y, and z satisfy this equation and this equation, then it satisfies the sum of those 2 equations. But it can't possibly satisfy the sum of those 2 equations, which is, let me just make that explicit, the sum of these 2 equations gives me x plus 3y plus 2z equals 14. Okay, if I take the sum. Okay, but it can't possibly be the case that, I'm sorry, I forgot this is a 2x here. Sorry. Okay, it can't possibly be the case that 2x plus 3y plus 2z equals 14 and 2x plus 3y plus 2z equals 13. It's not possible to find x, y, and z that satisfies both of these equations. Okay. Now we can see this same fact through Gauss's method. Remember, Gauss's method means that we eliminate variables one by one. All right, so eliminating x from the second equation means that I want to take row 2 minus row 1. If I do that, I get y equals 2. You can work out the algebra there. If I eliminate x from the third equation, I'll have to take row 3 minus 2 row 1, and that will get rid of the x. You can work out this algebra here. So notice these 2 equations say that y equals 2 and y equals 1. That's certainly impossible at this point. We can go a little bit farther to show the impossibility in very graphic terms. I can eliminate the y from this third equation by taking row 3 minus row 2, and I'll get 0 equals minus 1 for the last equation, which is a manifest impossibility. Okay, so we've shown through Gauss's method what we already saw above was that this system has no solution. Okay. Here's another example of a system that has infinitely many solutions. And how can we see that? All right, we've got 2 equations and 3 unknowns, and I think you may remember from your high school experience that in such case you will usually have infinite number of solutions. And so if we do variable elimination and eliminate the x from the second equation by subtracting row 1 from row 2, we'll get this system of equations here. Right. Now, I can take any value of z and get a value for y. And then with that value of y and z, I can get another value for x. So in fact, z is arbitrary, and any arbitrary z will give me a different solution. All right, here's another example of a system with infinitely many solutions. Okay. When we do elimination, you can follow these steps. It turns out that the last equation becomes a trivial equation. I get 0 equals 0. At this point, I have a system of equations very much like the system up here. I've got 2 equations in 3 unknowns. For any z, I can find a y, and for that y and z, I can find a x. Okay, so I have a solution for any possible z. All right, so let's describe the solution set. We've seen a case where the system has a unique solution. We've seen a case where the system has no solution. We've seen a case where the system has one solution. Okay? I'm going to stop here, and we'll continue this on the next video.